All right, so record. Thank you for reminding me. So we're now recording. We are now sharing my screen. Oh, come on. Oh, you're going to make me beg, aren't you? You're going to make me beg. Okay, so let's stop. Let me unplug my iPad. Plug my iPad back in. I'm glad I don't have to post these things on YouTube, because then everybody across the planet could pull up this video and see how bad I am at this. All right, okay, there we go. All right, so we were discussing the partition function, which within the context of the canonical ensemble is you simply take the Boltzmann weight, which is e to the minus beta times the energy of whatever state it is that you're talking about, e sub I, and then you sum over all values of I. Okay, where this beta is the inverse temperature 1 over kT. In the grand canonical ensemble, then the partition function is calculated again as the exponential of e to the minus beta ei. And then you also multiply by e to the beta mu n sub I, where mu is the chemical potential. And again, you sum over all i's. So notice that between the canonical and the grand canonical ensembles, this factor is the same. The only difference is you have this additional factor called the fugacity, which is little z, that you multiply by the Boltzmann weight. And what this allows you to do is in the canonical ensemble, the total n is a fixed constant, whereas in the grand canonical ensemble, n can vary. And in particular, what we're going to see is that the average total number of particles in your system is determined by the chemical potential. All right, so this is given by mu. So in other words, whatever the chemical potential is for your system, that is what determines the total number of particles in your, or total average number of particles in your system. Now, again, if you look at any individual instantiation of your ensemble, you can have fluctuations around that average. So some systems may have more particles than that, some may have fewer, but on average, the average total number is set by the chemical potential. All right, so now what you do in general is you take your, for a given system, you determine what the energy levels of that system are. You plug it into here in order to calculate your partition function. Once you have your partition function, then you use that to calculate the free energy, whether that is the free energy or the grand free energy. They're essentially the same thing, which we give the symbol capital phi. And that is defined to be the minus kBT log Z. Okay, so you, given your energy states, you calculate your partition function. Once you have your partition function, you use that in order to get an expression for the free energy. And then once you have the free energy, you start taking derivatives. Okay, and those derivatives allow you to calculate expectation values of various variables that describe your system. Okay, so for example, well, I don't want to, we're going to do an explicit example of this today. All right, so now that's the machinery we're going to use. And what we're going to do is we are going to apply this to quantum statistics. Okay, and again, what differentiates quantum statistics, or at least one of the things that differentiates quantum statistics from classical statistics, is that what you have is, instead of a continuous distribution of energies that your system can take on, in a quantum system, you are only allowed to take on certain discrete energy levels, E0, E1, E2, so on and so forth. Then, in general, as we've already talked about, what we're going to do is throw some particles into the system. They're going to fill up our energy levels. And in general, what we want to do is to calculate what are the average occupation numbers of each energy level, so on and so forth. Okay, so that is our goal. And that's what we're going to start doing in excruciating detail today. All right, so we're going to take a quantum system, we're going to throw in some particles, and we're going to try to calculate these average occupation numbers. All right, but now, it turns out that the answer that you get depends upon what kind of particles it is that you throw into your system, okay? And in quantum mechanics, there are two fundamentally different kinds of particles. Okay, so in quantum mechanics, there are, that's not how you spell there are two types of particles. Okay, these are what are referred to as the fermions. Okay, and what makes a fermion is the fact that it has half integer spin. Okay, so for example, an electron has spin, what was, man, I'm having a serious brain fart right now. So spin of plus minus a half, right? Okay, protons, neutrons, they also have spin a half. And you can also build composite particles out of these things. So for example, a nucleus that's composed of multiple protons and neutrons. So for example, if you look at helium-3, which is 2 protons and a neutron, that thing, and you sum up all the spins of the protons and neutrons, you will get a half integer. And hence, helium-3 acts like a fermion. All right, the other fundamental type of particle is what is referred to as a boson. Okay, and a boson has integer spin. All right, so for example, photons. All right, so photons, if I remember correctly, they have spin 1, I believe, because they are vector particles. The Higgs boson, as the name implies, is a boson. So the Higgs, so it has a spin equal to 0. It's a scalar particle. The strong and weak force particles. So that's the W plus and minus and the Z0 for the weak force. I believe these also have spin 1. I think they're vector particles as well. And the gluons. I think they're also spin 1 vector particles. There is hypothesized for gravity a particle called a graviton. Okay, so the fundamental object in general relativity is the stress energy tensor, right? So the Einstein's equation is G mu nu equals 8 pi T mu nu, right? So these things are vectors. That means that the graviton has to be spin 2. Now, so all these things we've lifted so far are essentially force carriers, right? So photons, W plus minus, Z0. So they're kind of immaterial force transferring kind of spooky ghost-like particles. But you can also have material particles that are also act like bosons. So for example, helium-4. So helium-4 is composed of 2 protons, 2 neutrons, and when you add up the spins of all these things in general, the state that it's going to occupy is going to have an integer spin, and hence helium-4, at least under some conditions, acts like a boson. Okay, so everybody is cool with the distinction between fermions and bosons, yes? All right, wunderbar. All right, so now we got to talk about how these particles behave. All right, so let's say that we have a particle sitting in space. So here's my particle. Okay, so now in quantum mechanics, the state of this particle is characterized by it being in some quantum state, which you would indicate as a ket. All right. Now, let's say I have two particles. Okay, so this is number one and this is number two. So that's psi1, and this one will be in some state psi2, like so. All right, and now these quantum states, they describe everything about the particle. So they describe its position, its momentum, its various quantum numbers, so its spin, whatever. All the information that describes the particle is contained within this quantum state. Okay, now when we talked before about classical mechanics, in classical statistics, we said that particles in our gas were undistinguished. Okay, and what we meant by undistinguished was that in principle, you can pull each atom out, paint a little number on it, and put it back. So in principle, you can distinguish particles from one another. However, when you actually look at a gas, you don't. All right, so in principle, particles can be distinguished. It's just that we don't. All right, however, in quantum mechanics, that is not the case. In quantum mechanics, particles are not undistinguished. They are indistinguishable. All right, which means that it is literally impossible for you to tell one particle from another. In other words, these little labels that I've put on these guys, no way, cannot do it. Okay, so in other words, if I have, let's just to make it clear, let me put my labels back. If I have two particles that are in a given quantum state, and I exchange these particles, all right, I should get exactly the same state, exactly the same state, exactly the same predictions from the wave function that characterizes that state. All right, so in other words, if you have multiple quantum particles, the wave function for your system, which I will call capital Psi, must be made up of combinations of the quantum states of each and their individual particles. And so let me just write it down so that you will appreciate what's going on. So what I have to have is combinations of psi1 and psi2. And I have to have the exchange as well. And then just for everything to be properly normalized, I have to multiply by 1 over root 2. All right, so in other words, this full quantum mechanical state for the system is composed of the individual quantum states of each of the individual particles, which has to behave in a certain way under particle exchange. All right, so now is when things are going to get a little complicated. So what I have written down here, this is correct for bosons. So this is correct for bosons. All right, so you can see that if I take psi1 and psi2 and I switch them around, okay, so if I exchange 1 to 2 and vice versa, I will wind up with exactly the same overall quantum state. Okay, now it turns out that fermions are a little bit different. Okay, now I searched for a very long time to see if there is a way to see why this has to be the case in an intuitive fashion. And as far as I can tell, that's not possible. Okay, so as far as I can tell, what I'm about to tell you requires the machinery of full-on hardcore quantum field theory in order to appreciate why this has to be the case. I don't have time to go into quantum field theory for you, so you're just going to have to take my word for it, all right? So it turns out that bosons, as I've written here, so this wave function, as I've written it down here, is completely symmetric, right? If I exchange 1 and 2, I get out exactly the same thing again. Now, it turns out because of quantum field theory, and it has to do with maintaining causality. So causality is kind of an important thing. And so to maintain causality in quantum field theory, it turns out that the multi-particle wave functions for fermions has to be anti-symmetric. And again, if you know a way to see this in an intuitive fashion, I would be super, super interested to see it. I looked for a really long time and I couldn't find anything that didn't require, hardcore field theory to appreciate why this has to be the case. Okay, so again, just take my word for it that for a fermion, the multi-particle wave function has to be anti-symmetric. And what I mean by that is this. Psi1, Psi2, just as we had before, except instead of a plus sign, it's got to be a minus sign. Okay, so here what happens is that if I look at Psi1, 2, and I exchange particles 1 and 2, what I get out is minus Psi2, 1. So if you switch the two particles, you get a minus sign. All right, so again, and I can't do quantum field theory in this course, so you got to just take my word for it that this is the case. Or if you have a good explanation, I would love to hear it. All right, so now let's think about what this means. Okay, so what does this mean? All right, so now let's think about Psi1 and Psi2. Okay, so and first of all, let's consider fermions. All right. So if two particles are in exactly the same state, so if we have two particles in the same quantum state, then Psi1 is equal to Psi2, right? And you can see that if you take this and you plug it in here to the general expression for an anti-symmetric multi-particle fermion wave function, you get 0. Okay, in other words, it cannot happen. All right, so in other words, fermions cannot occupy the same quantum state. It cannot happen. I'm doing my best. I don't know why I'm doing a Scottish accent now at this point, but what can I say? So multiple fermions have to be in different quantum states. Otherwise, the wave function vanishes and poof, everything disappears into thin air. Bosons, on the other hand, all right. So if you for bosons, if you say Psi1 is equal to Psi2, and then again, you come back up here to your symmetric boson wave function and you plug that in, you still get something that is not 0, right? So the fact that your multi-particle boson wave function is not 0 means that can happen. That is okay. All right, so in other words, bosons can occupy the same quantum state. Okay, so this is a fundamental difference in the way these particles behave. So by the way, so simply by saying that multi-particle quantum states for bosons have to be symmetric and for fermions have to be anti-symmetric, that tells you that multiple fermions cannot be in the same quantum state, and bosons can. And this is the Pauli exclusion principle, right? Okay, so the Pauli exclusion principle comes from the fact that multiparticle fermion states have to be antisymmetric. Boson multiparticle states have to be symmetric. And again, those things happen as a consequence of causality in quantum field theory. Okay, so what does this mean? Okay, and again, let me. So we've discussed now about just two particles. Now let's write down in general for n particles. All right, so for bosons, let me say n bosons. In general, you're going to have a multi-particle wave function that depends upon each of your particles. Okay, and if I exchange any of these particles, I get exactly the same state out. All right, so if I, for example, exchange R2 and R1, I get exactly the same thing. And in general, I can say psi, whoops, capital psi, R P1, R P2, whatever. Okay, so under exchange of any particles, I get exactly the same multi-particle wave function out. So this is for any permutation. Okay, P of integers, 1, 2, 3, all the way up to n. Okay, and as we said, this means that multiple particles can be in any quantum state, and hence, if we go back up here to our general idea of what a quantum system looks like, that means that these occupation numbers for bosons can be any value whatsoever. All right, so whatever quantum state we're talking about in alpha, if we want to calculate the occupation of that energy state, this can be anything. It can be 0, 1, 2, 3, anything. Okay, so this is for bosons. For fermions. Okay, so for fermions, if I have a multi-particle wave function, R1, R2, R3, up to Rn, and I exchange, again, particles 1 and 2, say, then I have to get a minus sign. Okay, and in general, if I permute some particles or combinations of particles, what's going to happen is that I get a phase factor out front, which is either going to be plus or minus 1. Okay, so depending on which particles I permute, I will get some plus or minus phase between the wave function. Okay, and again, this means, so this is again for permutation P. Okay, and so now, again, if we go back to our picture of a quantum state, what this means is that, so let me draw it again here just to be super explicit. If I have discrete energy levels like so, and I plop a particle into one of these states, that's it. No more particles. Okay, so if I throw in another particle, it cannot exist in the same state as the first one. So if I throw in another one, it's got to go into the next one. All right. So in general, whoa, blue, nice. So in general, the allowed occupation numbers for fermions is either 0 or 1. And that's it. Okay, you can't have an occupation number greater than 1. Okay, does that make sense? Okay, now, somebody might say, oh, well, but Professor Kuhlman, I remember when we talked about the hydrogen atom, for example, we drew energy levels like this, and we would always put 2 particles in. So I'd put 2 particles here, 2 particles here, 2 particles, so on and so forth. What? You don't know what you're talking about. And I'll say to you, no. I do know what I'm talking about, because what's going on here is that if to fit 2 particles into an energy level, they have to have different quantum states. And when this happens, the quantum characteristic that is different between these 2 particles is the spin. All right, so what's happening here is that if I throw electrons into the orbitals of a hydrogen atom, they will fill up like so, and one of them in one of these energy levels has spin up, and therefore in order to be in a different quantum state, this one has to be spin down. Okay, so this spin up, spin down, spin up, spin down, so on and so forth. Okay, so that's how it looks for fermions. And for bosons, the picture is we have energy levels, and fermions is just a wild orgiastic party, right? You just start throwing particles and it can be any damn thing you want, okay? So bosons are wild, unhinged characters, whereas fermions are, you know, straight-laced, uptight, Midwestern types. Not that I know anything about that. Okay, so them's the rules, all right? So that's the rules about how particles fill up energy levels. And now what we're going to do is to apply those rules to quantums. Somebody's saying something. What are we saying? Does this have any relation? Pauli exclusion principle, right? Right, as I've already said, that the symmetry and anti-symmetry of multiparticle states leads to the Pauli exclusion principle. And the next question the gentleman asks is, does this have any relation with Bose-Einstein condensation? My good man, that is exactly what we are going to show. All right, so it's exactly these rules. So what happens is when things get cold enough, all the bosons fall into the ground state, and that is a Bose-Einstein condensate. Now, you can't have that with fermions because of Pauli exclusion. You can't have all the fermions condensing into a single state. And hence, so it's not quite true that you can't have Fermi condensates. I don't recall whether we're going to talk about how that works. But Bose-Einstein condensation, that is, yes, exactly what we are talking about. All right, so now let's do it. Okay, so quantum, blue again. Quantum statistics. So now we're finally ready to do this. Okay, so now we specify some quantum system. We throw in some particles. We have to specify whether those particles are fermions or bosons. The type of quantum system that we are talking about is determined by what our potential is. So whatever the potential is that you plug into the Schrodinger equation, that's what determines your energy levels. How the particles fill up those energy levels depends upon whether they're fermions or bosons. And so given some potential function, you can determine what the energy levels are. Depending upon what type of particle you have, that describes how those states are going to fill up with particles. And then what you do is you take those energy levels and occupation levels and you use that to write down an expression for your partition function. And then once you have your partition function, you get the free energy and you start taking derivatives. Make sense? Fantastic. All right, so let's do it. Okay, and it turns out you can do this in general. I don't even have to specify which quantum system we're talking about. So I don't have to specify, are we talking about the hydrogen atom? Are we talking about particle in a box? Are we talking about harmonic oscillator. I don't have to say. All I have to say is that I know the system is quantum mechanical. Hence, I'm going to have discrete energy levels. And that's all you got to know. All right, so quantum mechanics means I will have discrete energy levels, which I will call E alpha. Now, the values of those E alphas will depend upon what type of system you have, whether it's harmonic oscillator, hydrogen atom, whatever your system is, that will determine what the E alpha are, but the E alpha will exist regardless of what your potential is. All right, so now what we want to do is write down, given that we have some discrete energy levels, write down what the Hamiltonian for our system is. Okay, now you'll recall that if I have some quantum state, whatever it is, and I act on it with the Hamiltonian, that assuming these are eigenstates of the Hamiltonian, what that gives me is the energy. Okay, so if this is psi alpha, then I get energy eigenvalues out. Okay, so in other words, the Hamiltonian is the energy, right? And the energy is what we need to know in order to calculate the partition function. All right. So let's assume we have some collection of E alpha, and into that E alpha, we're going to throw some particles. Okay. So again, let me just draw it. We have our energy levels. This is E0, E1, E2, E3, E4, etc. And I throw in a collection of particles. All right, what is the total energy of my system? All right, well, I know the energy of the ground state is E alpha. I've got 2 particles in there, so those particles contribute an energy of 2 E0. Here I've got 1 particle, so this is E1. This one gives me 3 E3. Oh dear, E2. This one gives me E3, E4, and then the total energy of the system is just the sum of all these things, right? Couldn't be simpler. In other words, in general, the Hamiltonian for a quantum system, you can always write like this. So it's H hat is equal to sum of E alpha in alpha hat, summed over all alpha. Now, what is in alpha hat? So in alpha hat is what's referred to as the number operator. Okay, and all that is that if I act on some quantum state with the number operator, that tells me the number of particles in that quantum state. That's it. Okay, so the number operator just counts the number of particles in the state. Okay, and so in general, these psi alpha, all they are just collections of specifying how many particles are in each state. Okay, that's all they are. It's just telling you how many particles are in each state. So each possible energy eigenvalue of your system just corresponds to different numbers of particles being distributed among your different energy states. Does that make sense? All right. All right, so we take our Hamiltonian, we act on our eigenstates. This will tell us the energy of our eigenstates. And in general, that energy is just equal to the number of particles times the energy of that state in each state. So I guess principal, this should be a sum over alpha. There we go. All right, does that make sense? So in other words, the energies, the different allowed energies of our system are just these numbers here. Okay, so it's just the N alpha times E alpha. Okay, so now we can use that information to write down our partition function. So now let's write down our partition function. Okay, now first of all, let me write down what it would be in the canonical ensemble. Okay, so in the canonical ensemble, that is with a fixed total number of particles. And you're going to say, wait. Last lecture, you told us that that isn't the way quantum mechanics works. And that's absolutely correct. And so now what I'm going to do is write it down, assuming that that is how it works. And what we're going to see is that it turns into a giant hairball that you cannot compute. And so allowing the number of particles to vary and moving into the grand canonical ensemble not only more accurately describes a quantum mechanical system, but it also allows you to calculate what this damn function is. It's a handy coincidence. All right, so in the canonical ensemble, the partition function is just equal to e to the minus beta times the sum over all alpha of n alpha e alpha. Okay, and then you sum over all allowed n alpha. Okay, and what this is depends upon whether you're talking about fermions or bosons. Okay, but now the catch is that you can't just do this sum. You have to do the sum with the constraint that when you add up all the number of particles, so here I just add up all the number of particles, that has to be equal to the total number of particles in the system. So again, this is the Kronecker delta. Which you write delta mn, which is 0 if m is not equal to n, and 1 if m is equal to n. So in other words, the sum only exists if the total number of particles is equal to the sum of the number of particles in every individual energy state. And when you try to do a sum with a constraint like this, oh boy, I know it's very difficult. It's very difficult to write down an expression in general for how to do an infinite sum like this. Well, for bosons, for example, it would be an infinite sum with a constraint that the numbers that you're adding up have to equal some specific value. It's very hard to do. Okay, so hard tears. And we're lazy scientists. We don't want to do things that are hard, right? We want our life to be easy. Okay, so the way that we're going to make our life easy, that is, we're going to be happy and barfing rainbows. I'm spending way more time on this than I should. Green, blue, violet. There we go. And my mouth isn't big enough. There. Barfing rainbows. The way you make it easy is you allow total n to fluctuate. Okay, and by allowing n to fluctuate, you do not have this constraint on your sum. That is, it makes it easier to do. And as we described on Wednesday, it also just happens to be how quantum mechanical systems behave. All right, so by doing this, what that means that what we need to do is to work within the grand canonical ensemble. where our partition function will also necessarily include the fugacity. All right, does that make sense? Okay, so let's do it. All right, so our partition function, z, I'm going to call this z sub n GC. GC reminding you that it is in the grand canonical ensemble. All right, so this is equal to the exponent of minus beta E sub n, let's say E sub n minus mu n sub n, and then we sum over all possible values of n. Okay, and then as we just described, we can write the total energy of the system in terms of the, so let me again just write it down. So this is beta sigma n alpha E alpha summed over all alpha. And then we multiply by the fugacity. Beta mu n alpha summed over all alpha. Okay, so in these we have to sum over the occupation numbers of every energy level in our system. And this other, so this is the sum over energy levels here and here. This sum here comes from the fact that, again, we're in the grand canonical ensemble and we're not specifying how many total particles are in our system. So we can have 0 particles in our system, we can have 1 particle in our system, we can have 2 particles in our system, we can have 3 particles in our system. You see where I'm going with this. So what we're doing here is we're summing sum over all possible total number of particles. Okay. All right, so now it turns out that this is the same thing. Again, you can write this out and prove it to yourself, but this is the same thing as this. So now we're just going to sum over all allowed values of our occupation numbers. Okay, of E to the minus beta sum over alpha in alpha E alpha, E to the beta mu sum over alpha in alpha. Same thing. Okay, and again, what this set of allowed occupation numbers is depends on whether you're talking fermions or you're talking bosons. Okay, now another way to write this is, so here I have 2 exponents that both have sums over alpha in their exponents. And so I can combine these 2 together and write this like so. Like that. Okay. And so now I have a exponent of a sum of exponents, right? So this exponent here is a sum, all right? And an exponential of a sum is the same thing as a product of exponentials, right? So another way to write this is as pi alpha sum over n alpha e to the minus beta epsilon alpha minus mu n alpha. And I don't like that. Let me write it like this. All right. Okay, so that's it. That's the answer. Okay, so this is our grand canonical partition function for n particles. All right, so now what we're doing here, so now this product you can see is over alphas. Okay, so in other words, this is the different energy state. You pick alpha equals 0, all right, and then for alpha equals 0, you calculate the partition function. Okay, then you do the same thing for the first excited energy state. So in other words, these things are the single energy level partition functions. Okay, and then you just take the product of all the single level partition functions to give you the overall partition function for all the energy levels of your system. Okay. All right, so now we have 1 minute remaining. The next thing we're going to do is to actually say, okay, what happens if we have bosons and what happens if we have fermions? But I'm going to wait to do that until next week. So in the remaining minute or so, I will ask, does anybody have any questions?
Is the n supposed to be outside of the exponent or inside the exponent?
I
mean the parentheses.
Inside the parentheses. Yeah, it should be inside the parentheses, I believe.
Because it's because you had it on the previous one. You had it inside, and on the second one you had a.
No, it actually should be outside, because this should also have n alpha in it, right? Because this is the energy. So the way I had it initially was correct. Okay, so I have the n alpha out here, and then the value of n alpha also determines the energy contained in that energy level, and it also is the number of particles in that energy level. That is the fugacity. Okay, does that make sense? Yeah, so you can see that up here I had n alpha times e alpha, and so when I combined them, I just forgot to write that other n alpha. All right, any other questions? All right, very good. So now what we're going to do on Monday is we're going to write down this partition function again, and then we're going to see what happens when we use the allowed set of n alphas for bosons and when we use the allowed set of n alphas for fermions. And you'll see that we get different statistics depending on what kind of particle you've got. All right, so until Monday, have a good weekend. Stay away from the coronavirus. And I will see you guys then. Adios.